So we have found one in the special case x prime equals f of x, that is the special case of 1D. We have found a method, first of all, for finding the equilibrium points. We just set x prime equals 0 and see what x's make that true. And then we also have a method for determining the stability of the equilibrium points, which is, let's go back to the logistic again. X prime equals bx times 1 minus x over k. And we have the equilibrium points 0 and k. And the way that we determined the stability was we chose what I'm going to call test points. Here's a test point, k over 2, and it turned out that the vector field was positive. Then we chose another test point over here, and let's say 2k, and it turned out that the vector field was negative. Now, the method of test points in one dimension works beautifully, and it works beautifully because of the very special property of one dimension that you are trapped. If this arrow is going this way and this arrow is going this way, there's no chance of you evading that arrow. You're trapped in between the two arrows, and you must go to that point. So the method of test points works beautifully in one dimension, but not so beautifully in 2 dimensions, and really not so beautifully in 3 dimensions, where it's almost impossible to see what's going on with the forest of arrows. So we want something better, but in order to do that, I want to make an observation. Let's go back to this state space and vector field here and realize that we have, let me use negative values here, we have an unstable equilibrium point here. We have a stable equilibrium point here. And remember what the 2 linear vector fields were. The 2 linear vector fields were x prime equals kx and x prime equals minus kx. And we're assuming k bigger than 0. What do they look like? Well, x prime equals kx looks like that. And x prime equals minus kx looks like that. So this is the remarkable point. This is this. This is this. In other words, even though this is a nonlinear equation, the equilibrium points are exactly the equilibrium points of linear equations. So this is a major, major point. Equilibrium points of nonlinear equations look like linear equations around that equilibrium point. And their equilibrium point character is either this linear equation or this linear equation. This is an example of a very general principle which you will see again and again. It's called the principle of linearization. It even has a fancy name if you absolutely insist. It's called the Hartman-Grobman theorem. And the theorem tells us that the equilibrium points of a nonlinear equation are linear equilibrium points, or behave like linear equilibrium points. And that's a major line of insight into these nonlinear equations. Now, far from the equilibrium points, the nonlinearity takes over and things can get crazy. But near the equilibrium points, these nonlinear equations act like linear equations, and their equilibrium points act like linear equilibrium points. So we now have a method, which is the method of test points. And I'm going to call that method number 1, test points. But I now want to introduce a different way of finding the stability of equilibrium points in 1D. And it's much more powerful, and it generalizes to higher dimensions. And that involves making a new kind of graph that we have not previously graphed before. So again, we're talking about a differential equation, x prime equals f of x. And because this is 1D and this is 1D, we can actually graph this function. And so we can graph f of x. Let's plot an axis. Here is the x-axis. And here I'm going to graph x prime. That is to say, I'm going to graph f of x. So we know how to plot f as a function of x. So for example, when x, in the logistic case, x prime equals bx times 1 minus x over k, you can multiply that out if it makes it easier. Bx minus bx squared over k. What does this look like as a graph on a graph paper? Well, you can get out your graphing calculators. We see that it's going to be a parabola because of the square. We also see that it's going to be an upside down parabola because the square appears with a minus sign. And if you graph it using CoCalc or your graphing calculator, you will see that the graph looks like that. That's a parabola. And this is f of x, and this is x equals 0, and this is x equals k. So this kind of graph we're going to call a vector field graph. And it's different from every other kind of graph you've seen before. It's not a state space. It's not a vector field. It's a plot of a function that is the one-dimensional vector field against the value of x. So this equation looks like that. Now, the minute we have a vector field graph, obviously finding the equilibrium points becomes trivial. What are the equilibrium points? They're the places where the red curve intersects the green axis, the axis x prime equals 0, which is the x-axis. So how many times does this curve intersect the x-axis? Twice. So there are 2 equilibrium points. We just read them right off the graph. But then there's another thing which is even much more interesting and much deeper. Now I want to find out if these 2 equilibrium points are stable or unstable. So let's look at the x equals 0 equilibrium point. Well, I know something. I can just stare at the graph and see this immediately, that for points to the right of the equilibrium point, f of x is positive. It's above the line. So if f of x is positive, that means the vector field is positive. On the other hand, to the left of the equilibrium point, The curve is below the axis. It's in negative values. So x prime is negative, and so it looks like that. So just by looking at this curve and seeing how it crossed 0, negative on the left, positive on the right, we immediately read off the character of the equilibrium point. This has to be an unstable equilibrium point. Correspondingly, let's go over to x equals k. Well, to the left of the equilibrium point, f of x is above the line, so it's positive. And then to the right of the equilibrium point, f of x is below the line, which is negative territory, so f of x is negative. And we have now established that x equals k is a stable equilibrium point. So this is a very powerful method of being able to establish the stability of the equilibrium points just by examining the graph of them and looking to see if it goes from positive to negative, from negative to positive, or from positive to negative for an unstable equilibrium point. But now we can even do something a little bit stronger, and this is going to be a very powerful move. We talked in the calculus section, we talked about the derivative of a function. And we weren't thinking about vector fields at the time, but we just said, hey, if f is any old function of x, then there are going to be derivatives of that, which are the slopes of the tangents. And the slopes of the tangents, if this is the function f, the slopes of those tangents are f prime of x, the derivative of x with respect to x. So we can now make the following observation. Here is a nonlinear function that went from negative to positive. I want to ask, let me get a different color. I want to ask, what about the tangent to that function at that point? Well, obviously, the tangent to the function at that point is going to have the same properties as the curved function at that point. If the curved function went from negative to positive, then the tangent has to go from negative to positive. And so we don't even have to look at the whole function, the nasty nonlinear function. We can just look at the slope of the tangent to the function here and the slope of the tangent to the function there. And if the slope of the tangent is positive, right here, positive slope, then the equilibrium is unstable. If the slope of the tangent is negative, here's a negative slope, then the equilibrium point is stable. So now we have said slope of tangent is positive at an unstable, and slope of tangent is negative at a stable.